After a detailed analysis of calculus of variations, now you will see that we will utilize this concept which we have developed in calculus of variations in solving the actual dynamical problems of classical mechanics. When you apply these concepts in classical mechanics to solve the dynamical problems, then actually it is known as variational principle. In this regard, first of all, we are going to explain a very important variational principle after the name of great mathematician Hamilton, and it is known as Hamilton's variational principle. So first of all, we will know what is Hamilton's variational principle, then we will prove it, and after that we will see its important applications. So let us see what is Hamilton's variational principle. Actually, this variational principle is not a general variational principle. It is applicable only to a conservative holonomic dynamical system. And this principle actually enables us to distinguish the actual path followed by the system from the neighboring paths. So what is this Hamilton's variational principle? Let us see. In fact, we state this principle in this way. I have mentioned here. The path actually traversed by a conservative holonomic dynamical system. Remember this. This principle, as I have told you, is applicable for conservative holonomic dynamical system. So when such a system is in motion or it changes its configuration, then the actual path traversed by it between the two time limits, let us say t1 and t2, in that condition, the actual path will be the path for which the time integral of Lagrangian between these two limits of time t1 and t2 must be extremum. It means just you can say that the path along which the time integral of Lagrangian L of the system between time t1 and t2 will be extremum. That will be actually the actual path of motion of the dynamical system. In fact, mathematically we say that integral from t1 to t2 L dt equal to I, and that is extremum. Here I is the extremum value of the integral of the Lagrangian L, and this is actually known as Hamilton's variational function of the path. And you know this L is actually Lagrangian, and you know this is T minus V, where T is kinetic energy and V is potential energy. So this is the basic statement. In short, I would like to state this principle in this way, that the path along which the time integral of Lagrangian L of the system will be extremum, that will be actual path of the system. In fact, in terms of calculus of variations, you can state this Hamilton's principle in this way, that delta I, which is equal to delta integral t1 to t2 L dt, must be equal to 0. But it is valid only when the variations with the variations 0 at t equal to t1 and t equal to t2. It means there is no variation at these two time limits or at the two end points. So as I have told you, this principle enables us to distinguish the actual path from the neighboring paths. So this is the statement of Hamilton's variational principle. I hope you have understand. Again repeating it, in terms of calculus of variation, mathematically you can say delta t1 to t2 L dt equal to 0. This is the Hamilton's variational principle. And this condition will be for the actual path. So in determining the actual path of motion of a conservative dynamical holonomic system, this principle is utilized and very useful. Now after this statement, now we will prove this principle. So let us see this figure. I have shown here three paths actually between connecting the points P and Q, and let us say at point P the system was at time t1, and at point Q the system was at time t2. Let us say actually this P and Q are endpoints, and a system changes its configuration from P to Q in this time interval t2 minus t1. And in this figure I have considered that this PRQ is actual path followed by the system, and these two curves PR prime Q and P double R prime Q, which I have shown by the dotted line, are actually the varied path or neighboring path of the actual path. And in fact you can say that our dynamical system changes its configuration from P to Q in this time interval t2 minus t1. Now to find to prove the Hamilton's principle, definitely we will have some conditions to be satisfied here. So what are the conditions that must be satisfied for the deduction of Hamilton's principle? Let us see here. There are two conditions. Two conditions to be satisfied for deduction of this principle. What are these two conditions? Actually these conditions are similar as you have studied in the calculus of variations. The first one is the delta variation of t, that is delta t, must be equal to 0 at the endpoints. So delta t equal to 0 at the endpoints. At the end points. When you say that delta t must be 0 at the end points, what does it mean? It means at time t1 the particle must be at P, and at time t2 it must be at Q. So the particle will be always at P and Q, whatever the path followed by the particle may be. It means if it is following the path PRQ or PR prime Q or P double R prime Q and others too, that particle must be at P at time t1 and must be at Q at time t2. So it means there is no variation of time at the end points. So in this small delta variation, this is a necessary condition that the small delta variation must be 0 at the end points. Now the second condition is what? There is no space variation at point P and Q. It means these 2 points P and Q are fixed in space. So if you take the position vector of any point on this curve by R, then according to this second condition, delta R must be 0. Delta R must be 0 at the end points. And when you say delta R must be 0 at the end points, then it means the point P and Q are fixed in space. So these are the two conditions which will be utilized in the small delta variation, and or you can say this is the property of a small delta variation, that delta t at the end point should be 0 and delta r should be also 0 at the end points. Now, taking these two important conditions for small delta variation, we will derive the Hamilton's principle first of all. So, for this, let us consider a holonomic conservative system acted upon by a number of forces, and among this system actually consists of a large number of particles. Suppose there is a system consisting of a large number of particles and it is acted upon by several forces. For calculation, we consider an ith particle. Let this is an ith particle, and this ith particle is, let us consider, acted upon by a force Fi. So Fi is one of the forces which act on our system. So you can write the equation of motion of this ith particle taking this force into account. When you say equation of motion, it means you have to define this Fi in accordance with the Newton's second law of motion. So, if Fi equal to force acting on the ith particle of mass mi, then its equation of motion. What will be its equation of motion? As I have told you, when you say equation of motion, it means we will write the second law of motion. So you know this will be Fi equal to mass of the particle times acceleration of the particle. Ai is acceleration of the particle, and you know this Ai can be written as dvi dt, where vi is the velocity of ith particle, and we can equally write it mi d2ri by dt square, and in dot symbol you can write it mi ri double dot. So this is the equation of motion of the ith particle. Now we will write the D'Alembert's principle, which we have studied during the Lagrangian formulation in previous lecture. And so what is this D'Alembert's principle? You know from D'Alembert's principle. D'Alembert's principle. What is this principle? You can see here. You have already studied this D'Alembert principle while we were discussing the Lagrangian formulation of classical mechanics. And this D'Alembert's principle actually is stated in this way: summation over I Fi minus mi ri double dot delta ri is equal to 0. Actually here you know this delta ri is what? You know it is called virtual displacement. This is virtual displacement of ith particle. And this expression you can write in this way. This is summation over I Fi dot delta Ri minus summation over I Mi Ri double dot dot delta Ri is equal to 0. So this is the mathematical form of D'Alembert principle. You know it. Now this factor Ri double dot delta Ri can be written in an alternative way. You can see here. Now Ri double dot and Ri double dot delta Ri dot delta Ri. What you can write it? Let us see here. We can write this term in this way. This is d dt of Ri dot delta Ri and minus Ri dot d dt delta Ri. You can check it. Actually, when we will differentiate it, then we will get this term and an extra term which will be this much. So after subtracting it, you will get this Ri double dot delta Ri. So you can check it. So this term can be written in this manner. Now, if we consider that there is a little variation along the actual path and the neighboring paths, then what will be this delta Ri? You can see here. So you can say if there is a little variation along the actual path and the neighboring paths, then you can write this delta Ri d dt delta Ri will be what in this condition? Our aim is to find it. And in this condition, what will be this delta Ri? Delta Ri means Ri prime minus Ri. Actually, Ri prime is the position vector of a point on a varied path or neighboring path, and Ri is the corresponding position vector on the actual path. You can see here, if we consider that this point has position vector Ri relative to some origin, then this point will have position vector Ri prime relative to the same origin. So this prime has been used for the neighboring path, and in this condition, if you have defined this delta Ri in this manner, then what will be what we can write d dt delta Ri? Let us see here. So in this condition, you can write then d dt delta Ri. This can be written as d dt and delta Ri. We have defined it in this manner, Ri prime minus Ri, and you can write it d Ri prime dt minus dri dt. And so you can see this is actually the small variation of dri by dt when one moves from the actual path to the neighboring path. So we can write it that delta variation of dri by dt. But you know dri by dt means ri dot, so you can write that this d dt delta ri is equal to delta ri dot. See here, dri by dt is equal to ri dot. So say this is equation. What will be the equation number? Actually we can write, say this is equation 2 and this is equation 3. So now we will make the use of this equation 3 in equation 2. See here, in this equation 2 here is d dt delta ri. Now in the light of equation 3 we can write this d dt delta ri dot. So after use of that equation 3 in this equation 2, what now the equation 2 will become? Let us see here. So you can say using 3 in 2, using 3 in 2 we have, see here, this will be ri double dot delta ri. This will be equal to what? This is d dt ri dot delta ri minus ri dot delta ri dot. Say this is equation 4. Now we will use this equation 4 in the first equation, which is actually the D'Alembert principle. See here, as in this equation the term ri double dot delta ri is present, and we have evaluated the value of this ri double dot delta ri. So now let us substitute that value of ri double dot delta ri in this equation 1. So using equation 4 in this equation 1, what we will get, you can see here. So using equation 4 in equation 1, we get, let us write it in another page for convenience. So you can see in the first equation, the first term is summation over I fi dot delta ri and minus summation over I mi, and there is ri double dot delta ri, and we have already evaluated the value of ri double dot delta ri here. So let us substitute this value in that equation. So this is d dt ri dot dot delta ri and minus ri dot delta ri dot and this will be equal to 0. This is equal to 0. Now we will simplify this equation a little bit. You can see here the first term I am just writing again summation over I fi dot delta ri and minus summation over I mi. You can see here this is d dt ri dot delta ri and the last term, see here, this ri dot delta ri can be written in this manner. You can write it 1 over 2 delta of ri dot square. You can check it and this will be equal to 0. Simply when you will take the small change that will be of ri dot square, that will be 2 ri dot delta ri and that 2 and 2 will cancel out, so we can write this ri dot delta ri equal to half delta ri dot square. You can write it. Now see here, we can write this equation as summation over I fi dot delta ri and let us combine this term to the last term here and this will be plus summation over I half mi delta ri dot square and take this term in RHS. So after bringing this term in RHS, this will be equal to summation over I. As you know, in classical physics, mass of a particle is treated as constant. It is not a function of time. So you can take this mi inside the operator d dt. So we can write it summation over I d dt summation over I d dt mi ri dot delta ri. You can write it. Now see here, the first term is fi dot delta ri. Now this second term, in this second term, as you know, mi is not varying here, so it can be inserted inside this operator delta, which represents the small delta variation. So you may write the second term in this way. You can take delta variation of summation over I half mi ri dot square. You can write, because mi is not varying, so we can operate this operator delta before mi2. So, and this RHS remains at ease. You can write it in the same manner. This is summation over I d dt mi Ri dot delta Ri dot delta Ri. Say this is equation 5. Now we will recognize that the two terms in LHS. What are these two terms? You can see here. So see here. The first term is summation over I Fi dot delta Ri. You know this is actually the total work done by the forces acting on the system, because Fi dot delta Ri, that will represent the work done by the force Fi on the particle I. But when you take summation, it means this is the work done by the forces acting on the system. So we represent it by the symbol W, and this is work done by the forces acting on the system. This is the total work done by the forces acting on the system. And what is this summation over I? Half mi Ri dot square. You know, actually Ri dot means velocity Vi of the ith particle. So half mi Ri dot square represents the kinetic energy of ith particle, and when you sum up it, you get the kinetic energy of the system. Or you can say that this is actually the sum of the kinetic energy of the all of the particles of the system. So this gives actually the kinetic energy of our system. So we represent it by the symbol T, and this is equal to kinetic energy of the system. But as I have told you earlier in the statement, that this principle is valid only for a conservative holonomic system. So our system is since conservative, so definitely forces acting on this system are conservative forces, and you know the work done by the conservative force is equal to, in fact, the negative of the change of potential energy of the system. So this work done W, which is work done by the conservative force, this must be equal to negative of the change of potential energy. So you can say that as the system is conservative, as the system is conservative, system is conservative, so this W must be equal to minus delta V, where V is potential energy of the system, you know it, of the system. So when we will use these values of W and kinetic energy T in this equation 5, what will be our result? You can see here. This first term is equal to now W, and W is equal to minus delta V, and this second term will be delta T. So now we can write the equation 5. So now equation 5 becomes, what will be now this equation 5? You can see this will be actually equal to minus delta V plus delta T, and this is equal to what? See the RHS of this equation. This is summation over I d dt mi ri dot delta ri. So this is summation over I d dt mi ri dot delta ri. Now actually we will integrate this equation between the time limits t1 and t2. So integrating this equation between time limits t1 and t2, what we will get, you can see. So integrating between the time limits t1 and t2, what will we will get? You can see this will be integral from t1 to t2 minus delta v plus delta t dt equal to summation as integral from t1 to t2 summation over I d dt mi ri dot delta ri dt. Now let us simplify it. You can write the LHS in this manner. This is integral t1 to t2 delta of t minus v dt, and this is equal to what will be this integral? You can see this is integral from t1 to t2 summation over I differential of this dt and dt. You may assume that cancel out, although it is not mathematically correct, but to understand you assume like that. So this is differential of mi ri dot delta ri, and you know the integral of differential of this much. Differential of this much will be what? This will be simply summation over I mi ri dot delta ri. So you can say this expression. Now this integral delta of delta t minus v dt, it can be written as delta of integral t1 to t2 t minus v dt, and this is equal to what? This is summation over I mi ri dot delta ri, and the limits for t1 you may write point P, and for t2 you may write Q. Now first of all we will see what will be how I have written this delta t minus v dt equal to delta t minus v dt. How we have written it? You can see it here as when you write delta t minus v dt, let us suppose that this is actually the product of two functions t minus v and dt on which this operator delta is operated, and this can be written as delta of t minus v times dt plus t minus v delta of dt. But you know this delta of dt can be written as differential of delta t, because these two operators may be interchanged. But as you know that delta t remains 0 at the end points, so d of delta t will be equal to 0. And so you can write that this delta t minus v dt can be written as this much. So delta t minus v dt is simply equal to this much, and therefore I have taken this delta variation outside of this integral. Now see here, as I have mentioned earlier in the conditions which must be followed for the derivation of this Hamilton's variational principle, that this delta Ri must vanish at the endpoints. So you can see this delta Ri will be 0 at P, and this delta Ri will be also 0 at Q. So in RHS, the term in RHS will vanish at these points P and Q, and hence we can write this expression in this way. You can see there as delta Ri vanishes. Vanishes means it is 0 at P and Q. So what will be your result? You can see, so delta integral t1 to t2 t minus v dt, this will be equal to 0. Now you know this t minus v is what? T minus v, you have already studied in Lagrangian formulation that this is Lagrangian of our system. This is denoted by L, and this is Lagrangian of the system. Since this is just the basic definition of Lagrangian, it is that kinetic energy minus potential energy of the system. Therefore, you can write now delta of integral t1 to t2 L dt equal to 0. And you have seen in the statement that this is nothing. This is simply the Hamilton's variational principle in terms of calculus of variation. And if delta of integral t1 to t2 L dt equal to 0, then you can say that this time integral of Lagrangian is extremum. So you can say that integral t1 to t2 L dt equal to I, and this equal to extremum. And you have seen in the statement that this is nothing. This is simply the Hamilton's variational principle. So this is Hamilton's variational principle. This is Hamilton's variational principle. So you have seen what is Hamilton's variational principle, what are the conditions to derive it, and after following those conditions and the D'Alembert principle, you have easily proved the Hamilton's variational principle. I hope you have understand all of the steps here clearly. So go through this video, and if you feel any trouble, write in the comment box. I will definitely explain your doubt.